Okay, so in this video we are going to learn FIFO from scratch. If you're a beginner, this video is going to help you massively because we are going to learn each and every concept. We are going to start from sunburst paper which you can get online, and then we will see questions on FIFO for interviews, and again we will see the RTL level code of FIFO as well, which has literally everything. Even if you're advanced guys, since we have codes and everything, this is going to help you massively. Now let's begin. So why do we need FIFO? Because suppose there's a data and there's a clock domain crossing, and we are passing the data from a slow clock domain to a fast clock domain. Do we need FIFO? No, because whatever the data which is coming to be sampled is coming from slow clock domain, so the faster clock will be able to sample it. In that case, we can use a double flop synchronizer, and depending on MTBF, which is mean time between failure, we can use triple flop synchronizer or double flop synchronizer, or in industry we do use Pessimistic synchronizer as well. So we don't need FIFO in that case. However, if the data is coming from fast clock domain to slow clock domain, in that case the slow clock won't be able to capture the fast data. So in that case, suppose the data is coming at high speed, now clock is sampling at low speed, so there would be some data which will be left without reading. So we need a FIFO buffer, so that we can store those data. So what we will do, that we will start storing the fast data from fast clock domain to a FIFO buffer with the faster clock, and with a slower clock we will read that data, and whatever data is left in the burst size, that will be used for by the read clock to read it again, even after the write clock, which is the faster clock, has stopped writing the data. So that's basically why we need FIFO. Moving ahead, as you can see, the paper says FIFO is often used for safely pass data from one clock domain to another. We have covered this. So there's this thing that never write into full FIFO and never read from empty FIFO. What is empty FIFO? Empty FIFO is, if we go over here, now this is the FIFO code. Okay, this will probably explain you. Okay, so if the FIFO is empty, when FIFO is empty, when read pointer is equal to write pointer, when we will reset it, it will be equal. Now if I open my notes, you see over here we have empty condition, never read. Yeah, now think of it this way, that if we are going from FIFO full will be okay, FIFO empty. Now we are writing on a FIFO buffer, and then the read pointer chases us down. So at that point there is nothing in the FIFO. So when the read pointer chases the write pointer, that's the empty condition. And when the write pointer, say it revolve around, and when it chases the read pointer, that's FIFO full. Now I know I'm going abruptly, so I'll just get back and just read my notes so that I can explain everything. To determine full and empty condition, obviously we need to compare. So we need to compare read and write pointer. But if we open a FIFO image, let me just do Google search. FIFO. Let's see what we got over here. I guess there will be some image. Okay, we have to do VLSI over here. VLSI, and then we will get a FIFO diagram over here. Yep, this is what I was looking for. So let's just open it in new tab. Okay. So over here you can see it's now, as I said, there is a write pointer, and then there is There's a write pointer and then there is a read pointer. These are there in different clock domain. You can see clock over here, again clock over here. Now coming back, you can see that over here, by the way, this is a really nice site. You can obviously, whenever you need to read a blog, you can come here and read that. So if you see in the write clock, we have write pointer, and we have in the read clock we have read pointer, but we need to use that. I mean, in order to see the empty condition or full condition, we need to use those two pointers with each other. For that, we need to synchronize it. Now again, how we synchronize that? So we are passing it to a synchronizer, and then we are comparing. So as I said, what is full? When the write counter chases the read counter, it becomes full. Now who is chasing write? So just to memorize this stuff, whoever chases in his clock domain, we are going to see it's full or empty. So we will see empty. So for empty condition, read chases write. So we are going to check it in write clock domain. For that, we have to synchronize write pointer in the read clock domain. So as you can see, it's getting synchronized over here. And this trick I just use for remembering it, so that I don't have to analyze it in my brain all the time. So you can see it's getting synchronized, and again it's getting synchronized to get full condition. And again, this is a dual port RAM in which we put the data, and from here we read it. So this is just, we are putting the data. So when I'll show the RTL, it will be just a registers, nothing more than that. Now getting back, now there's this question. We need to put the write counter into the write counter into the read domain, and read counter into the write domain. Well, this sounds easy, but the pointers are multi-bit. We cannot do multi-bit synchronization. So in order to do because the reason why we cannot do multi-bit synchronizer in binary, I'll just show you. There's a reason for it as well. There will be a reason. Okay. Is there anything I can do? Okay, let me just tell you. So okay, I'm just going to tell you verbally. So what happens that suppose it's a 2-bit binary number, 00011011. Now if we go from 00 to 11, what will happen is there's a 2-bit change. If we are doing a double flop synchronization with that, then what will happen that there's a possibility. So when we do RTL level simulation, there's literally no there's no gate level delay. So gate level is basically delays of standard cell and nets. There's no such delay, so we are fine. But when in reality, when chip comes, or when we do a gate level simulation, there are delays. So how the transition will occur? It might go from 0 to 1, but again there are different gates, so it will have different delays. So it at one point it can be 0, so start with 00, then it can go to 0 1, and then it can go to 1 1, or it can go to 1 0, and then it can go to 1 1. So you see, we are not sure about the value. I mean, it can be 1 0, and there's a point that we might capture 1 0, which is wrong. We should not capture 1 0 because of multi-bit synchronization. Now since I am going deeper, I'll just search why multi-bit synchronization is bad. You can see definitely get bad. We will see the Reddit post. You will see you have to consider multi-bit. You don't know they will arrive at relative to your receiver. Each bit have slightly more or slightly less delays. This means synchronizer might see change in one bit earlier than other. That's what I said. Now obviously that's a problem, and we don't want problem in our life as well as in our design. In order to do that, we use gray code. Now gray code is something, a type of code in which it changes by 1 bit. So you see this is a gray code, it goes 1 0, there's only a 1 bit change among each of the level. Now the only thing about gray code is, suppose it there's a delay, and it suppose it is going from 1 to 2. In that case, what will happen, that there's only 1 bit change. It can either stay at 1, so in that case there's no problem, because we will read the same, we will read it again from 1, or it can go to 2. So in both cases there's no problem. We are suppose if it would have been a binary code, what will be 0 0 1, and then it's 1 0, it can go to 1 1 as well. We don't want that. What we want, so in that case obviously it will be wrong, but in this case, since it's a single bit change, it will work. So you can read about why we are using gray code and all. So that's going to help. I don't want to make it a super long video. Coming back to the basic, let me open my notes over here. Yep. Now we have understood to determine empty and full conditions, we have to synchronize it, and most of the things we understood. So now what we understood, that in order to do the comparison for full and empty, we have to convert it into gray code and then synchronize it, because in that case there is only a single bit change which is happening. So that is all good, no worries. So there's no problem whatever we are facing with binary. Now have I left anything? No. This is MSB, rest of bits are 0. So yeah, there's one more thing which I want to add over here, and this is a bit tricky to understand. Now, and actually watch Paul Franzen's video on this. That is really good. Now over here you see, for read it's fine, because I mean, if I see over here, for read it was fine, we can directly see that both are equal or not. But I mean, we just need to see both are equal. But for write, now if we see over here, it is revolving. So write pointer has done one revolution and read pointer is over here. Now if so how would we discriminate it from full condition? Because again it's the same. It can, if we just take suppose there is a 4-bit depth which is required for like it will go from 0 to 15, and we just need 4-bit to represent it. So for full and empty the conditions are same, so we add one extra bit in order to have this revolution. So when it has revolved, the right pointer will be incremented by 1. Now the MSB will become 1 and the rest of bits will be same. In that case what will happen is that it will be fine. I mean, we just need to see that MSB is inverted and rest of it are equal or not. So synchronized read pointer might not represent current value of actual read pointer, but right pointer will not go beyond sync read. Okay, so there's another concept over here. So there's a concept that we might if we might I mean, there is a problem which might happen, that we might overwrite. We might write in a full FIFO. So with this we can never write on a full FIFO because we are having a pessimistic approach. So over here this is a kind of advanced concept. So read pointer is getting synchronized into write domain, so that's going to take 2 clock cycles, and by that time, since we are continuing reading, the read pointer will reach to higher value, and obviously we are comparing it to write pointer. So write pointer is actually behind, is always behind read pointer. So we are not going to do overflow. That's what I've written over here, that it won't count beyond it, because it is not, the synchronized read is not actual value, but it is the value 2 clock cycles before that. Same thing, we won't read from empty FIFO, because again we are doing the same by same logic. So because anyway we are synchronizing right pointer, so that's the the value with which we are comparing its 2 cycle previous value. Now this is called pessimism in empty and full condition. So, and there's again all concept of almost full and almost FIFO depending on the band. Now we have covered this. This is also covered. This is also covered. Now empty and full, again I think you have understood it, that what exactly we are doing over here. Now over here uh, I have written some code which we'll go through later, and I'll be adding this in description so you can go with it. But I think we can just see how exactly we can calculate FIFO depth, which is a very important interview question. So FIFO depth is basically number of data items which are left without reading. So whatever data, I mean the read counter is a slow clock, but it will be reading some of the data which is written by write clock, which is the faster one. But there would be some data which is left. So that data we need to store in the FIFO depth. So it's very simple. We just need to see. So n is FIFO depth. N divided by 1 by write is 1 write time, and then if we multiply it, it will get total write time. And then if we divide it by write 1 by fr, then we will get number of data which will be read by which will be read by read pointer. So we just need to subtract it from total number, and then we just need to subtract it from total brush size, and then we will have FIFO depth. This is very simple. And then that's it, I guess. And obviously this is so now just let's see which I guess we have covered this, and then these are questions which you can go through now. Coming over here from binary to gray conversion. Now we just see if we shift the binary to right side and XOR it, we will have the gray code conversion. The RTL is very simple, and for I guess binary, gray to binary, there will be a different type of conversion. I guess we have for that also I have code. Yep. So this is the code for that. Now there will be a code over here, I guess. Yeah, this is gray to binary. So for this you need to use genvar. Generate, I think I've written it somewhere. Yeah, you can see over here genvar is written. So generate, this is a Verilog code for it. So we need to use for loop and left shift, and this is bitwise XOR operation. Now we have covered this mostly, and again there's one more important thing, that we do not need to convert the gray data back to binary. So that going to cost which is going to cost us extra hardware. We don't want that. So what we are going to do for that is basically, I guess we have covered the whole nodes in sort. Now let's just go to the RTL code. I guess, yeah. Going to RTL code, we can see what we are doing. So this is the data which is coming, and this is, so if this is write increment and this is read increment, whenever this is 1, we are going, when this is 1 we are going to write, when this is 1 we are going to read. This is write clock, this is read clock, this is RSTB, and this is data full data, this is data full and data empty. Now we'll wrap this video just in 5 minutes, so stay with me. So over here now, I guess this is the synchronization which we are doing. Now over here obviously the data is like d size is the data, is like number of bits of the data, and obviously this is write clock, this is read clock. Now coming over here, we are giving FIFO is full or FIFO is empty as well. And then over here, now let's just get back to, and we are converting, as I've showed you, that we are just shifting it left and XORing it. This is binary to gate conversion. Now this is the memory. So this is the SRAM which we saw in the picture. This is the memory which we have declared. Now over here you can see we are making, I mean this part is, I mean we don't need to actually fetch 0 at reset. We can just have X over there, because I feel like this is extra hardware, but we can have it. Over here we don't need to, whenever FIFO is full we don't need to write it, and whenever read is incremented we will write it, and obviously we will increment the write pointer. Now we have to synchronize. Now again we have to synchronize the gray conversion of read pointer in write clock domain, which we are doing over here. Now again over here we are again synchronizing the write pointer in read clock domain, and if FIFO is empty we are not going to do anything. So this is this part, and obviously we are incrementing the read pointer as well. Now the only thing, this code looks very simple. The only thing which we are concerned about is the empty and full condition at this point of time. So this is also very simple, friends. We just need to compare the gray part of read pointer, which we have already converted, already calculated, and then the synchronized write pointer in read clock domain, just this. And this part of code is also not required. If we delete it, this is also correct. Anyways, over here now there's this thing. Understand this code. What we are doing over here, we are comparing the inversion of first to MSB should be equal to read clock pointer in write clock domain, and rest of it should be equal. Now this is a bit confusing. If we go to the paper over here, so there will be a full condition, FIFO full, yep, generating full condition. Now over here, yep, now we will just read that the full comparison is not as simple as empty comparison. The pointer that are 1 bit larger are needed to address the FIFO memory buffer are still used for the comparison, but simply using gray code counter with an extra bit will not do the comparison is not valid to determine full condition. So this problem is there. We cannot just invert the MSB and then compare it as we would have if we would have converted it back to binary. So in this we will invert both the MSB and LSB, first and second MSB, and we will have it. So if we invert both, then there is no problem, as we can see over here. So we have to invert first and second MSB as well. That's what I have done over here, and this is a correct code. This is going to work, and this is it. That's what all you need to know for FIFO. Thank you guys.